So this talk will be a survey, and I want to speak about Herglotz-Nevanlinna functions, realizations in a very broad sense, just how to describe these functions, characterize these functions, and then based on this generalization. So I expect that everybody here knows some parts here, but I hope that there is nobody who knows already everything, so that there's something for everybody. Okay, so we have to start with the definition. It's day one, so we still can do that. We have a function that is defined in the upper half plane, complex valued, and it's called Herglotz-Nevanlinna if the imaginary part is larger or equal than 0. And we know the theorem that here it was already used, but I want to recall it, of course, going back to Nevanlinna, Herglotz, Picauer, that the function that is defined in the upper half plane and complex valued is a Herglotz-Nevanlinna function if and only if it can be written in this way. A real constant, a non-positive constant times theta, plus the integral term, where this is integrated against a measure, a positive Borel measure, such that, so the measure is such that this function here is integrable. So the Lebesgue measure might be an example for that. And we know that the A, the B, and the mu are unique in this representation. So I guess all of you have your simply put it in the book. All of you have your favorite examples. So let's take look. I want to write down some, even if they are very simple. So examples. So my first one is, so to say, the one who is building up all the other functions, namely minus alpha zeta minus t0, where alpha is a positive number and t0 for the moment is a real number. So this corresponds in the integral representation to the point measure at the point t0. H2, my function h2 of theta, is equal to the constant I. Then h3 of theta, we have already seen today, minus 1 over theta plus I. So we can think about it, theta is in the upper half plane, plus I is still in the upper half plane, 1 over is in the lower half plane, minus is in the upper half plane again. A little bit more advanced one, tangents theta. Here we have already infinitely many poles, so then the measure is a little bit more interesting. Of course, there are much more interesting, and I guess you will hear some from Henrik, I think. So I don't want to write down more. But I want to say which are not. So these are Herglotz-Nevanlinna, but not. Let's say Q1 of theta, something like this, but with a sign change. So let's say 1 over zeta. This maps into the lower half plane, of course. Or Q2, 1 over theta squared. Independently of if I have plus or minus 1 over theta squared, this is not a Herglotz-Nevanlinna function. One can see this easily from the integral representation because there is this term 1 over t minus theta. So towards the real line, the singularity can only be, cannot be more than linear. Not much more, at least not quadratic. Okay. Yes, and the third example, because I want to look at it later on, tangent theta, which was a Herglotz-Nevanlinna function, minus I, which also was a Herglotz-Nevanlinna function. But the difference is not. Okay. So it was already pointed out today, So if you look at your function, it was defined in the upper half plane. If you look at the integral representation, there is no problem to plug in a point in the lower half plane. Okay? So you can extend your function via the integral representation to the lower half plane. Since these coefficients here and the measure is real, what you will get is basically this one here. So it's like conjugating. So you get the function, the extended function, which will have this symmetry property. Okay? So for my functions, for my examples here, what would this extension be? So for the first one, it's simply the same function. There is nothing complex or nothing is happening here. For the second function, if I extend it, so if this is for theta in the upper half plane, then I have to take minus I for theta in the lower half plane. And now we have such an example where this extension to the lower half plane, according to the integral representation, does not give you an analytic continuation over the real line, because there you would expect to continue it like the constant I. Or here, this was in the upper, this was in the upper half plane. But if I make it in the lower half plane, it will become this one. So this was the function in the that appeared in the first talk, basically, of this type. And this is connected to the fact how the measure looks like, that there is mass on the whole axis, so you cannot go over these singularities. But in the first talk were these holes there on the real line. Okay. So I'm thinking about an Herglotz-Nevanlinna function either defined in the upper half plane, but then I know it also in the lower half plane, always the symmetric version. Or I'm thinking about it as a function that is defined in the upper and the lower half plane, but then with the symmetry. Okay? So what I want to do now is to go through several equivalent ways of characterizing Herglotz-Nevanlinna function. So, So this is a big theorem collecting knowledge of 100 years. You have a function in the upper half plane, complex valued, and then the following statements are equivalent. First, this function is a Herglotz-Nevanlinna function, by definition, analytic, and I've written it here in this extended version. The imaginary part is larger or equal than 0 in the upper half plane, and lower or equal than 0 in the lower half. This first, we can rewrite this in really a trivial way. Namely, so I have given it the same letter because it's really the same. The function is analytic, but whenever you take a point in the lower half plane, then the equation f of theta is equal to this point in the lower half plane has no solutions in C++. Yeah, obviously, because the function maps into the upper half plane. But we'll come back to that. So now already the next point has appeared. These first characterizations were properties of the function in the upper half plane for all theta. But the next one here is only, so to say, the limit on the boundary. This is because of the maximum principle. It is enough to have here that the function is analytic, and the boundary values of the imaginary part are larger or equal than 0 for all t on the boundary of the domain. So for every real point and infinity. So this is important. And it might happen that this limit is infinity, but then it has to be plus infinity. So it has to be positive, so non-negative. So if we look at our examples here, for instance here, the imaginary part of Q1, so the imaginary part of Q1 of x plus iy is equal to the imaginary part, so what this was 1 over so x squared plus y squared, x minus iy. So we have imaginary part y minus y x squared plus y squared. As long as x is not equal to 0, then this tends to 0, of course. But if x is equal to 0, this tends to, from the upper half plane, this tends to minus infinity. Okay, so this one point where it is not satisfied makes the whole function not a Herglotz-Nevanlinna function. And in the same way, we could check this squared. Yes? So if we check the squared, the imaginary part of q2 of x plus iy is equal to minus 2xy divided by x squared plus y squared squared. As long as x is not equal to 0, there's no problem. This goes to 0. But if x is equal to 0, now you think, oh, it looks also 0. But this would, so if here is 0, so if we take this limit here, it would be 0. But we have to take a non-tangential limit here. So here I was a little bit, I didn't say this. Zeta goes to zeta 0 non-tangentially. So if t0 is here, so it means that this limit has to be taken inside some angular domain, something like this. So, and in this case here, if you take, for instance, x is equal to y, if you make an approximation like this, if you approach from here, then you get here out squared, but here you get to the power 4. So it again explodes with a negative sign. So also this function q2 does not satisfy this condition in one single point. Yeah? Maybe at this, yeah, maybe. Yeah. Afterwards, if it is a function, we know that it exists, but at this point we don't know. Yeah, you're right. Okay. Next on my list, something that looks a little bit stronger. So the function is analytic, and this kernel here is positive definite. What do I mean by that? This kernel is positive definite. So you take this n h of zeta I, zeta j for some number zeta I and zeta j in the upper half plane, and you build the matrix ij from 1 to, let's say, capital N. And then all these matrices should be positive definite. Should be, yeah, so the quadratic form should be positive semi-definite for all choices of these points zeta I, zeta j, and also for independently how many such points you choose, how big you make your matrices. Okay? If you take simply one point, this reduces to the imaginary part. Okay? So it's obvious that if the function satisfies this condition C, then it is an Herglotz-Nevanlinna function, but it's also the other way around. So if it is an Herglotz-Nevanlinna function, only the positivity of the imaginary part, together with the analyticity, already implies that this kernel is positive definite. To be honest, I don't know how this can be proved without the integral representation. I really need this to show this. Integral representation. So this is further equivalent to that the function can be written in this way that we have just discussed before. Let me remind you, the a was a real number, the b was non-positive, and the mu was a positive measure, which can be infinity, can be an infinite measure, so the measure of the rule line could be infinity, but if you weight it with this factor, then it is finite. So it is straightforward if we rewrite this term here as one quotient, then we get some expression times this factor 1 over t squared. And if we then put together this mu together with this new factor, we get this representation. So this is now only this one here rewritten, and here I've collected the factor and the measure. So the new measure is now a finite positive measure, because this condition here is satisfied is exactly the same as that the integral over this new measure is finite. So there's nothing happening. But will be important for the generalization to write it in this second way. Okay. Then what we call a realization, or it's an operator representation. This is the following. So a function is a Herglotz-Nevanlinna function if and only if there exists a Hilbert space H, an element in this Hilbert space, a self-adjoint operator, maybe multivalued operator, but this is not so important here, and then some point in the upper half plane, so that the function can be written in this way. And the important part is here. Here's the resolver. We have a self-adjoint operator in a Hilbert space, so this resolvent here is a bounded linear operator in the upper half plane. So, and then, okay, here we add something, this is not so important. And then we take the inner product multiplied by this element V and take the inner product with this element V again in the Hilbert space. And then there is some, to make it really an equivalent. But the important part is this resolvent here. Okay. So I will come back to this. Then what I will not speak so much about, but which you, or many of you, know much better than me, Herglotz-Nevanlinna functions are exactly the transfer functions of passive systems. So there is a convolution operator with an element with a distribution y, and then the Laplace transform of this impulse answer evaluated at theta divided by I multiplied by I will be a Herglotz-Nevanlinna function. It has appeared in the first talk where there were additionally a reality of the system assumed. Then the function would be symmetric, as it was in the first talk. But if you drop this reality, then you will get all the Herglotz-Nevanlinna. And then finally, here on my list, I've mentioned an exponential representation. So this is now, the function is exponent e to the power. And this one here is again a Herglotz-Nevanlinna function, but a little bit particular. So there is no linear term. And the measure here is absolutely continuous with respect to the Lebesgue measure. And here we have a density. So this is a positive function, which has some growth condition, which I have not written down here. How do you get this? Well, the logarithm, if you cut correctly, is a Herglotz-Nevanlinna function. So if you take a Herglotz-Nevanlinna function and take the logarithm of it, then it again will be Herglotz-Nevanlinna function. But this one is nicer, because the imaginary part is bounded now. And if the imaginary part is bounded, then the measure is absolutely continuous with respect to the Lebesgue measure. And if you use this, and then you write it as e to the power logarithm of the original function h, you get this representation. Okay. So we'll see this slide several times during the talk. We'll come back to this. First, I want to pick out some of these relations directly. So have a closer look. So there was this Herglotz-Nevanlinna function is equivalent to that it can be written as an integral representation, as equivalent that there is this self-adjoint operator. Okay? So how can we see that these things are equivalent? Well, the first from A to D, this was the theorem that I just mentioned before. So this is, so to say, the hard part. Then from D to E, it's almost trivial. So you have a very good candidate for such a space. Oh, sorry. So there's an integral representation with the measure mu. So you can pick as a Hilbert space the space L2 with this measure mu, with respect to this measure mu. And then as A, as the operator, you take the multiplication by t, by the independent variable. And if you choose the v, I think like 1 over t minus theta 0 bar or something like this, you basically get out, if you plug this in here, you get out the integral representation. The only problem is that the linear term will not appear here, but this you have to add additionally, then you get a multi-valued operator. So this is a detail that I don't want to discuss. But from the integral representation, you can build such an operator. And then if you have an operator representation, it is straightforward to check that this function actually is a Herglotz-Nevanlinna function, because it's analytic, and if you write down the imaginary part, you will end up by an inner product or a norm in the Hilbert space, which is non-negative. Okay, so why do we have these operator representations if they are basically the same as the integral representation? I would say because they give us other tools and other ways of looking at the function. But also from the other side, we can realize when we are dealing with a Herglotz-Nevanlinna function if they come from an operator. So for instance, alternative operators could be second order differential operators on a half line or so. So then this would be the corresponding function would be called Titchmarsh-Weil function. Or we could have canonical systems. This would then be a way to, again, the Titchmarsh-Weil coefficient, again, would be a way of characterizing the functions, but I have left it out here. Okay. Then there is this operator representation that I just named. And then there is this transfer function versus passive system. And there is also an operator, but this is a convolution operator. Okay. So, and I guess some of you know, but I don't know, what is the relation between the R from the passive system and the A, the self-adjoint operator for the operator representation. I mean, I can calculate this in some examples. We have seen something today, but really in general, I don't know how this is done. I'm sure somebody knows it. Maybe one word to the operator representation. So if we look at the examples over here, so here the operator representation is very simple. This is just one-dimensional space. Okay. Here, the measure is a Lebesgue measure, and we could use this construction that I have just told you. But here, it is maybe a little bit more interesting, because I guess if you look at this, you would think rational function, one-dimensional representation. But this is not the representation that I'm looking at, because I want to have a self-adjoint operator in a Hilbert space. So if you realize this in a one-dimensional space, you have a multiplication by minus I. So this is not self-adjoint. So there are some differences there, how you view your thing. I want to have this self-adjointness here. Okay, then I want to mention something about the sum rules that we have seen in Matt's talk today. So I pick out just one case. Matt has written it in more generality. So you have your Herglotz-Nevanlinna function, and we say that it has an asymptotic expansion of order 2n infinity minus 1 at infinity if it has such an asymptotic expansion. So it can be written in this way. Namely, there exist real numbers, the coefficients here, such that we have this behavior as theta goes to infinity, again, non-tangentially. So this means in such form. Okay. And the sum rule then tells you that the principal value of this kind of integral is equal to the corresponding coefficient in the exponent in the expansion. Okay, so I was expecting Mats to write it approximately this way, but he was more precise. So more precisely, what this short version here means is this one here. So you have two limits actually to take. First of all, this plus 0 is the limit where the y goes to 0. So you integrate not on the real line, but close to the real line, parallel, and then take the limit afterwards. And then secondly, there might be singularities. Here, this is for the positive n. If you take negative n's, then there would be a problem at 0. So I've written here this is a little bit too much, but it doesn't matter. So we take first the problem point out, integrate everything, and afterwards let the epsilon go to 0, symmetrically. It doesn't matter that this is epsilon and this is 1 over epsilon. These are completely independent, but it is important that it is symmetric with respect to 0. So it's this principal value. Okay, and Maxence asked me to show a proof for this. So that's why I was thinking to show a proof of this. Sorry, I forgot. I wanted to mention something important. So this is the sum rule, but there is a little bit more of a statement. Namely, if for some integer, this limit here, so basically the left-hand side in the sum rule, exists, if this limit exists as a finite number. So this is if and only if the function has an asymptotic expansion up to this corresponding order. Okay? So the limit and the asymptotic expansion, this is equivalent. So let's start by this expression. So the limit epsilon goes to 0, the limit y goes to 0, the integral epsilon less than x less than 1 over epsilon x to the power n, imaginary part of h of x plus I y dx. Okay. So what we can do, of course, is first to substitute the imaginary part here, and this we do from the integral representation. So what we get here is that this is equal to the limit epsilon goes to 0. Okay, I'm a little bit quicker now. I write it like this. Limit y goes to 0. This integral. And then we have this integral. This is over. Sorry. The imaginary part, first we have what's coming from the linear term, plus, and then the integral part, which is 1 over pi y divided by x minus t squared plus y squared d mu of t, and then dx. Okay. So now first we see that this term here, if y goes to 0, so this term disappears, so we don't have to bother about this at all. And then we have these two integrals. And the first step is that we can check that via Fubini's theorem we can exchange these two integrals. Okay? So let's change them. X to the n, y divided by x minus t to the squared plus y squared, dx, and then d mu of t. Okay, so now what we want to do is to move the limit from here into this integral. And this is okay by dominated convergence. So then here one has to work a little bit to put this into here so that we can estimate this integrand here with something that is integrable independently of y. And then we can move this inside by dominated convergence. And then this can just be calculated, so there is not so much magic in this. So that's why I don't do the details here. So what you have here is you have a function, and then you have this kind of kernel here. And then you take the limit, you integrate against it, and then take the limit with y going to 0. And here together with this pi, this is a kind of, how's it called? Yeah, but approximation by identity, approximation of the identity, precisely. So what you get here is this function here, but the only problem here is, technical problem is that the function in some sense is not a continuous function because you cut here, yes? So it's 0 up to minus epsilon, then it becomes this function, and then, yeah. So what you get is, you get back your function, but on the jumping points you get the mean value of the function. So what you get here is that this is then, so let's call it xn times, so how should I call, I think I called it phi of x, where phi of x is this function. So this is equal to x to the n as long as then it is 0 outside, and then here it is the mean value. So if epsilon is equal to x or 1 over epsilon. Yeah. Okay, so I understand what I mean. It's a bit. And then we have this d mu of t. And now, if epsilon goes to 0, then what we have here is that the function, our function here, by epsilon, our function here is monotone in each x, because yeah, it's jumping from 0 to this point, and that's it. So what we have here is we can use monotone convergence, and we can move this inside, and what we get is the integral over r. Now we get t to the n, but there is only one point, namely we get never at 0, so all these functions are 0 at the point 0. So what we don't get with us is the point measure of mu. So it will be d mu 0 of t, where mu 0 is the original mu minus a possible point measure at the point 0. So this would then be mu of 0 times delta 0. So this is a point measure at 0. Okay, so what we have seen now is that this limit is the same as this moment here. And then in the next step, we have to come from the moment to the asymptotic expansion. And this, there is not happening so much, so I'm not doing this now. But it's simply writing down the expansion, start with the first terms, write down the expansion, and then you see what you get is basically you end up with a moment. And that's it. Okay. So, yes? No. Yeah, in some sense, yes. So the first term, the B1, you get as a limit. Yes? So you look at the difference of these terms, then at the limit. So you're not expanding the kernel in the expansion, in the integral. Okay. So now we have seen everything that we wanted to say about the Herglotz-Nevanlinna functions. Now we are on the way to generalization. So my idea is now to look at this long list of equivalent properties and see them simply as properties, and then go them through and look what can we generalize and what do we get then. Of course, this will not be equivalent then in general. But so let's have a look. So I was thinking, which one should I start with? Because so lead in different directions. So I decided to use the one that I was seeing first, namely number C, this kernel property. So for Herglotz-Nevanlinna functions, this kernel is positive definite. So here we can make a generalization. So this was done in the 70s by Krein and Lange. A function which is defined in some subset set of the complex plane, complex value. And it now is, if it is meromorphic outside the real line. So there are possibly poles, but it turns out that there can be only finitely many then. And the kernel now is assumed to be has kappa negative squares. This means that this matrix that we had here now has at most kappa negative eigenvalues. And kappa is minimal with this property. So if you have a function of this type, then this is a generalized Nevanlinna function by definition. The examples that I have had here, this one and this one, are both of this type. This one is not of this type. This class is actually connected also with two of the other characterizations that we had before, namely to the this with the number of solutions and with the operator representation. So the following theorem holds. For a function q, the following are equivalent. Q is an n-kappa function. This is equivalent to if q is meromorphic in the upper half plane. I forgot here, in the upper half plane. And for every point in the lower half plane, this equation has now exactly kappa solutions in the upper half plane. Okay, so the only difference to before is that before there was no solution, now there are kappa solutions. And this is further equivalent that we have again an operator representation. It looks exactly the same. The only difference is that the space is a different kind of space. So now we don't have a Hilbert space here, but we have a so-called Pontryagin space. So a Pontryagin space is you have a vector space, you have an inner product on this space, but it's not necessarily positive definite. But it can be indefinite. Pontryagin space means that whenever you have a subspace that is non-positive, then it is at most kappa dimensional, so only finite dimensional. And then under additional assumption of minimality, then this negative index of the space and the kappa here, they will be the same. And based on this, quite a while later, it could be shown that this is further equivalent, that the function admits a factorization, so that it is a usual Nevanlinna function multiplied in a symmetric way by a rational function. And from this one, you see, for instance, that this is a generalized Nevanlinna, but actually also this. Yes. So what you see from here is the picture that you should have here is there is the singularities on the real line. They come, the green ones, they come from the usual Herglotz-Nevanlinna function. So you have that where the measure has mass, if you want to think like this, or where the original operator had a spectrum. And then there are finitely many exceptional points. These are the poles of this rational function. Or if you think in the operator representation, these are eigenvalues of the A, but particularly in the following sense, that the eigenspace is not the positive subspace with respect to this inner product. So they are special, but there are only finitely many. Some rules do in general not work, and the problem is basically that you get a singularity in. So you cannot look at integrals of this type because this imaginary part can explode. So the real line. And I'm trying to sell these classes to Mats for years, I would like to have interesting examples where this is. So I understand that the whole class is too large, and I understand that these non-real poles make problems. You said that this is not good for the stability. But what about if there are only these exceptional points on the real line? Okay, let's go back to our big theorem. Let's look at the integral representation. So in the integral representation, we have these parameters a, b, and the measure. What can we do there? We can define a quasi-Herglotz function. So it's a function of the same type, looks exactly the same, but the parameters have different properties. The a and the b are allowed to be complex, and the measure is allowed to be a complex measure, which implies that this is a finite measure, and that's why I needed to write the representation in this way. Okay, it's straightforward to understand that this happens exactly if your function is a linear combination with complex coefficients of Herglotz-Nevanlinna function. So you take simply the measure and separate it in real and imaginary part, and each one in positive and negative part. So we have used these functions to approximate systems. So Guillaume will have this in his poster or something of this. And we have looked at these functions, characterized them analytically, and this hopefully will appear now soon. And I've spoken about this in Banff, so I decided not to take up more about this here. There is a realization in a Krein space, and this will appear actually in the poster of Christian. But it is still open to characterize how the corresponding operators are. So to say, these operators give me exactly quasi-Herglotz functions. This we have not solved. Some rules, in general, no. So we have looked at exactly for this function here. This is a quasi-Herglotz function. And for this one, the sum rule doesn't hold. Already the first part doesn't hold. So I think the integral exists. No, the asymptotic expansion exists, but the integral doesn't exist. But under certain conditions, you can say yes. Namely, if, so to say, in some sense, the singularities of these functions that are involved are separated, or yeah, let's put it that way. Okay, back to our long list. What more can we do? This one here. It was that the imaginary part towards the real line has to be larger or equal than 0 in every point. And this leads to a class that was introduced in the 80s, actually motivated by electroengineering applications, which we don't really understand. But anyway, a function which is of bounded type, it means quotient bounded analytic functions. Herglotz-Nevanlinna functions are of this type, but now we have to assume it additionally. And that this limit that we're looking at before is still larger or equal than 0, but now for almost all points on the boundary. So you see the example that we have looked at here, this belongs to this class. And yeah, I've written this in this way. So in this paper, they are looking at the Caradeo-Dori case from the unit disk into the half plane. So and then they call this for pseudo Caradeo-Dori functions. But now we already have generalized Nevanlinna functions. We have quasi-Herglotz functions. Now pseudo becomes too much. So we need a new name, but we don't have a new name yet. But in these original papers, they have also shown that these functions are exactly those of the form, again, a factorization. A Herglotz function times something which can be more general than a rational function now. So it's a kind of called density function, which I don't want to go into the details. But you can think about it. It is a class that generalizes the generalized Nevanlinna function. There exist realizations in Crine spaces. This is the poster of Christian. And we are on the way to characterize them. So this is ongoing work. Back to our list. Do I have a little bit of time? This goes very quick now. If I look at the operator representations, I can make here additional assumptions on the A. I can take away this with a Pontryagin space with finitely many negative part finite dimensional, but then I have to add something, and these are other classes which are possible to look at. This one, Mats mentioned it. This would be very interesting, but I cannot say more than that. Here, one could also channelize by allowing here more general things, and this should be actually be understood. So here one could characterize it. So I think this doesn't give so much more. Yes. Oh, sorry, here. Yeah, the last what I wanted to mention here is that we have started with functions from C plus to C. All of them were of this type. So there is also a possibility to generalize. First of all, we can make the values of the function more general. Then almost everything works in a very similar way. Or we can look at several variables. And this would be another talk, so I decided not to say something about this here now. But there is an integral representation, but there are interesting features there because not all measures are allowed. And this also makes a problem with the sum rule. There are operator representations either only for a subclass or in some kind of multiplicative way Mitya has done. Yes, and this is the main question here. Which questions in this context are interesting from your point of view, in particular for these functions of several variables? So let me finish this by an advertisement. So together with Yvonne, we have put together some facts on Herglotz-Nevanlinna functions and picked some applications which we think are typical, and this will appear somehow as a chapter. So it was one chapter, but then had to be separated, so because it's too long. So then it's only left to say thank you. Yeah. I don't know. Yeah. Yeah. I don't know, maybe it's more complicated. I don't know. Passivity is evaluated. Because it's a sign property that is not the case anymore. Yes.
Very nice. Maybe I should. Could you add the response
what?
For the generalized? Multiply with. It's a sum.
So I mean, it depends a little bit. You see, if you look at these two examples, so for the second one, it is positive on the real line, but only, not negative, but only at one point it is violated. So something like this you would like to have for. You would not allow to.
I mean, in some ways, it has a.
The rational function. But the rational function is positive because this is symmetric. So this is the Q is equal to R of theta times H. Okay, you can write it like this as well. H of theta. So if you are on the real line, then this is positive on the real line. It's only. Yeah. But the imaginary. Yeah. But the imaginary part as a whole is not necessarily, yeah. No. Sorry? Yes, yes. Well, yeah, if you have, so if you have on the real line, if you have an interval where you have absolutely continuous spectrum and the density is analytic, then you can continue over this interval in an analytic way. Yeah, exactly. So if you extend this function, the H2, H3, by simply looking at the first, yeah. If you take this as a definition also in the lower half plane, except at minus I, then you would get something that where you have extended in this way, analytical. Yes. 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 I mean, for me, this way of the symmetric extension comes from the operators, because there is this operator which has the spectrum. Oh yeah, so. Lebesgue measure. It's a Lebesgue measure. Yes.
Interesting one. Herglotz. Hopefully this.
Yeah. I forgot to mention something, because I put this proof of the sum rule, yes? And there was dominated convergence and so on, but here was the monotone convergence. So if you have the problem is with the monotone convergence, that here you might have terms that cancel each other. So and that's why you cannot go this step here. In the case of that the measure is, let's say, a signed measure, positive part and negative part. And that's why the sum rules don't really work. And even if they work, I guess it is a bit tricky to use them, because I mean, you cannot, if you take an interval also, you cannot estimate, because you might lose something that is negative. So you don't know, you need to know more in order to be able to estimate in the correct direction, I guess.